Hello, guys. Welcome back to Maths on African Motives. We are still on our power machines and six, and this is Nozzles from the question paper, which was written in August 2022. So we just want to see how we're supposed to answer or attempt this typical question. If we check, most of these questions are just like a repetition, but the way that you be given some of the information, that's why I tend to come up with the same questions because of how the information is given, but how to calculate and this is just the same. So power machines is all about the information that you are given, the formulas and how to manipulate your formulas, only that. All right, let's see. How can we answer this one? 2.1, define the Mach number as it pertains to nozzles. All right, what is what we refer to as the Mach number considering the nozzles? All right, so we know that the Mach number is referred to as what? The ratio of the velocity. This is just a ratio of the velocity at any point along the nozzle to the velocity at the throat. That is what you refer to as your Mach number. So that is referred to as is the ratio. So you can just say this as is the ratio of the velocity. All right. So we've got the velocity there at any point. That is the most important part. It must be taken at any point along the nozzle. Along the nozzle to the velocity. All right, to the velocity in this case at the throat. To the velocity at the what? At the throat. So that is what you refer to as the Mach number. Okay, so that is 2 marks just to explain this. Then we are given 2.2, a convergent divergent nozzle. All right. So this is a convergent what? It expands a gas from a pressure of and temperature of to a pressure of. All right. So this is, let us just have a simpler sketch here. That's 2.2. Remember, this is a convergent, divergent. As I said, you're going to have something of this nature where we have got this side representing the inlet. So this is our inlet. This is our outlet or the exit. All right, you can refer this as the exit, and this is the throat. All right, remember this is our throat. So we have got 1, we've got C for the critical values at the throat, and we've got 2 for the exit or the outlet. So there we are given the pressure of what? 800 when it is entering 800 and the temperature 600 degrees Celsius. So we've got the pressure at the inlet. So this is P1 at the inlet, which is 800 kilopascal. All right. And also the temperature of 600. So if we add 273, this is going to give us 873 in what? In kelvins. All right. Remember the conversion to kelvins. And also we are given here to a pressure of, which is at the exit from the inlet to the exit. So we've got P2 there, which is given as 175 kilopascal. All right. And what else are we given here? We are given that the nozzle's overall efficiency, the overall, not to say the divergent or the nozzle of, this is the overall efficiency and the Mach number is. All right. So there we are given overall efficiency for everything. All right. So the overall efficiency is given as 89%. And also we've got the Mach number, which is given as what? As 1,3. Okay. Remember, I said there's a ratio of velocity at any point to the velocity at the throat. So you must be able to use that Mach number. So there we are given the area at the nozzle exit. At the exit is what? 7,45 square centimeters at the exit. So we have got the area at the exit, which is A2 at the exit. You've got the area. That's 7,45. All right. 7,45, and it's given in square centimeters there. So it must be also be able to convert to what? To square meters from square centimeters. All right. What else are we given? We are also having the adiabatic index. All right, so this is under adiabatic. All right, so the adiabatic index and the gas constant are off. So this is the adiabatic index and this is the gas constant. So we've got 1,4 and 0,87. So that is the adiabatic index. It's gamma. So gamma is 1,4. And the gas constant, which is R in that case, is given as, remember, we are given as 0.287. This is 0.287 kilojoules per watt per kg Kelvin. All right, then what else do we have here? The inlet velocity is what? Negligible, meaning to say the inlet velocity is not considered here. It's considered as 0. So the inlet velocity is at what? It's at 0 meters per second. So that's the information that we have. Let us try to answer our questions. The first question was 2.1, calculate on 2.21. The constant pressure specific heat capacity. Remember, this is our CP. We've got CV for volume. Then this is CP for what? For constant pressure, and to 4 decimal places. So where and how can we calculate our CP in this case? Where do we have this CP? Where do we have our CP? Let us minimize a little bit. All right. So that's 2.21. We want to calculate CP, the constant pressure heat capacity. Okay, so this one, we have to play around with the formulas that we are given. We have to play around with the formulas that we are given. All right, let's check what we have. We've got the gamma. We've got R here, only that. Only this. We do not have CV. All right. Let's check here. We've got what? The gas constant, only we do not have CV. All right, so let us take this from our formula sheet. If we check on page number 1, there is a formula which consists of R there, the gas constant, that R is equal to CP minus CV. And also for gamma, that gamma is equal to CP over CV. So let's try to penetrate through these two formulas. All right. We have R in this case, that's 0.287. So meaning to say 0.287 is equal to CP minus CV. Okay? So here we want CP. So we can have CV as the subject so that we substitute this one in terms of CP. So you're going to write CV in terms of CP. So you're going to make this the subject. That will be CV is equal to, already there's a CP this side. We transpose the 0.287, it subtract. So this is the expression for CV. Why are we making CV the subject? Because we do not want this. So we have to eliminate the CV here so that our formula is going to be gamma, which is the gamma that we are given, 1,4, is equal to CP, which is the one that we want to calculate. Remember, you're supposed to calculate CP. So we are going to make CP the subject. All right, over the CV from this part of CV that we had as the subject, we're going to have this as CP minus 0.287. Then we can calculate our CP. It's now an equation that we have here. So how can we solve this? We're going to cross multiply this side and this side. So 1,4 is going to multiply everything. All right, so let's multiply by 1,4. This is 1,4 times CP, which is 1,4. CP is minus 1,4 times this value. It's going to be something like 0,4018. If you multiply this, this is equal to 1 times CP here, which is CP. So we can transpose the CP this side so that it becomes a negative. The 0,4018 to the other side, it becomes a positive. So if we subtract 1,4 minus 1, it's going to be 0,4. So that will be 0,4. CP is equal to, we transpose this to the other side, it will be 0,4018. So to find CP, what do you think we're going to do? Just going to divide by 0.4 both sides. So divide by 0.4 both sides. We've got what? CP. So this is our CP, just a manipulation and playing around with the formula. So this was going to give you 1,0045 to 4 decimal places, all right? This is CP, which is measured in kilojoules per what? Per kilogram Kelvin. All right. So that is how we could have calculated our CP, meaning to say if you want CV, we can come back here and substitute this and subtract. We've got what? We've got our CV from there. But the question was to calculate CP. All right. Then the other part of the question, that's 2.2. 2. The absolute actual. Then we also have the isotropic temperatures. So we need the actual and the isotropic, as well as the velocity at the nozzle exit. At the exit, meaning to say at the point 2. So at point 2, this is what we want, 2.22. Let us just save our solution here. So at the exit, we want the absolute temperature, which is, we are supposed to calculate T2, and the isotropic value, and what else? The velocity, is that velocity there? And as well as the velocity, all right? So the velocity is just the velocity. So this one, they are talking about C2 there at the exit, remember. So that's the idea there. So how do we calculate T2? If you still remember, I talked about this idea of T2, that T2 is taken from the original values of the gas, from the inlet to the exit as it is. From our normal calculations, remember, from our formula sheet, there's a formula there on page number 1, which says that T2 over T1 is equal to V1 over V2, which is equal to P2. In terms of pressure, it's P2 over P1 to the exponent of n minus 1. So in place of n, we put gamma there. So it's going to be gamma minus 1 over a gamma. So we want T2 in this case, we're just going to multiply by T1 this side, just to move the brackets. It's just 1, so there's nothing there. So if you multiply by T1, we're going to remain with T2. So T2 is going to be given as T1 into P2 over P1 to the exponent of gamma minus 1 over the gamma. So as you can see, it's a straightforward question, this one, all right? This one is a straightforward. We have got T1, everything is there. T1, we have got our T1, remember? Our T1 is 873 in kelvins. So that's 873 in this case, all right? That's 873 into P2. Remember P2 at the exit, that's 175 over P1, the inlet pressure, which is 800 kilopascal. So you're going to divide by 800 in this case, all right? To the exponent of gamma minus 1, remember gamma, it's 1,4. So this will be 1,4 minus 1 over the same gamma, which is 1,4. So that was going to give us the absolute temperature, T2, at the exit, and that's 565,494 Kelvin. All right. That's the idea there. Then all right, so we started with the absolute there, which is just like the actual temperature, right? Then we've got the isotropic, this one. The isotropic now, because we do not have like the formula direct, because we now have the absolute, but we can take advantage of the efficiency. Remember, I said the efficiency carries actual values and also the isotropic values, this one, and is the overall efficiency. So you can take that as an advantage. It's an overall efficiency. Since we want to calculate what? Since we want to calculate T2 bar, all right, we want to calculate T2 bar. We have to consider the formula with efficiency where there's T2 bar and also where there's what? Where there's T2, because there are so many formulas for efficiency there. Let me show you from the formula sheet. This is what we have for efficiency here. So where there are temperatures, as you can see, there are so many formulas. So we need where there is T2 and T2 bar. Where there is T2 and T2 bar, it's here. But do we have TC? No, we do not have TC. This one, T2 and T2 bar is there, but we have T1 and T2, we have T1. Yes, we've got T1. So you're going to take this formula because we've got T1 so far. So you can take advantage of that. Take the formula where the information is there. Don't force a formula which is not applicable because it's there. Use the formula exactly because the information that you are given is available there. So from that formula, it's given that the efficiency is given as, sorry, I want this one. The formula for efficiency is given as T1 minus T2 over T1 minus T2 bar, which is the one that you want for the isentropic value. We can even make it the subject of the formula. All right, so you're going to cross multiply. This is over 1. So it's efficiency times this value. All right, so if you multiply by efficiency, it's going to be what? Or you can divide by efficiency. All right, let's leave it like that. T1 minus T2 bar like this is equal to T1 minus T2. So since I do not need this, I can divide by efficiency. I remain with T1 minus T2 bar is equal to, if I divide by efficiency, it means I'm also dividing this side by efficiency. So it's T1 minus T2 over the efficiency. So to find T2 bar, it means I'm going to transpose it this side so that it becomes a positive that side. So that means T2 bar will be equal to what? T1 is going to remain this side minus this fraction as it is, which is T1 minus T2 over the efficiency. So this is a single term, all right? It's a single term, like a single expression. So therefore, we can calculate this. T2 bar is equal to T1. We have T1 from our information, which is 873. So it's just like mathematics. And now change of subject, this one. Change of subject, this and that. So you see that power machines is all about the formula and how to manipulate the formula. All right. So we can say this is 873 minus, again, we're going to have T1, which is the same 873 minus T2. We calculated the absolute temperature here, 565,494. Everything over what? Over the efficiency, the overall efficiency as a decimal. Remember, our overall efficiency was what? 0.8. 0.88 or 0.89. Overall efficiency is what? 0.89%. So it's 0.89. So you're going to divide by 0.89 as a what? As a decimal. So that's 0.89. All right. So that is our overall efficiency, this one. So it can work at any stage. So that is going to give us the value of T2 bar, which is 527.488 Kelvin. Okay, so that is the isentropic value. All right, at the exit. But it's not ending there. We also need the velocity there at the exit. All right, so the velocity at the exit, I said this one, you can use the formula. All right, so that is C2 at the exit. We've got the formula straightforward from our formula sheet. But you have to take the best one. We are dealing with a gas. So this is the formula here that you're going to use. This one for C2 at the exit with H1 and H2 is for what? When you're dealing with the steam, where we have got the enthalpies there. So this is the best formula to use. So it states that C2 is given as, so that is the square root of 2 times 10 to the exponent of 3. 2 times 10 to the exponent of 3 times Cp, which is our constant pressure, heat value, heat capacity, sorry, into T1 minus T2. That's T1 minus T2 plus C1 squared, which is the inlet. And you're told that the inlet velocity is negligible. That's a 0 there. So that C2 is going to be equal to the square root of 2 times 10 to the exponent of 3 times Cp. Our constant pressure is the one that we calculated. Let's hope I did not remove it here. That was the first value that we calculated here. That was 1,0045. All right, so you're going to take that value in kilojoules as it is. So that's 1,0045. 1,0045 0045 times the temperature difference T1. Remember T1, guys, we talked about this. T1 was 873. We also used it here, T1 here, 873. So this is 873 minus T2. T2, we have it, T1 minus T2. T2 is what? 565,494. The difference in temperatures, we had this before, plus C1. Remember, we do not have the inlet velocity. We are told that it's what? Negligible. So whenever it's negligible, it's a 0 there. So that was going to give us the velocity at the exit, which is 785,9895. So it's going to be 990 to 3 decimal places. All right. In what? In meters per second. Remember, this is velocity. Velocity in what? In meters per second. Okay. Then also, so the other information, guys, I'm gonna remove it because there's now a lot of information here. You just have to take it back if you want to see properly the values where we calculated them, because I'm gonna remove some of this information here. All right, so let's see the other part of the question, which is 2.23. On 2.3, they are now saying the velocity in meters per second, the actual absolute temperature, and the pressure at the nozzle throat, at the throat. So we need the velocity at the throat, which is C, like this, at the throat, the actual absolute temperature, the temperature at the throat, and the pressure at the throat. All right, so these ones are an advantage because we have them from our formula sheet. So we're not gonna waste much time. I talked about this previously, and I said whenever you are now at this stage, you have to be very, very glad because they are given from your formula sheet as they are. So there's nothing to worry about. All right, so what is it that you are given? Let's start with the velocity. So the velocity, we saw that we have got so many formulas for velocity here. There is this one for the temperatures here. But if we check, this one is limiting away. We have got CP, we have it. T1, we have it, but we do not have TC. We haven't calculated this and we need it here. All right, if you check, we also need TC later on. So this one is not working. So which one are we going to use? All right, there's this formula from your match number. All right, it states that the match number is equal to, because we are given the match number there. Remember, we said the match number is the velocity at any point to the velocity where? At the throat. Remember, that was my definition there. All right, the velocity that we have at any point, meaning to say it can be at 1, it can be at 2. That is the velocity at any point. So in this case, the velocity that we have at any point is which one? Have we calculated the velocity before? Yes, if we take note about the second condition, there is a velocity that we calculated at the second condition. I just hope I did not remove it. All right, maybe I removed it. But we calculated the velocity at the second condition, C2, this one. So meaning to say, we are going to use any velocity with the calculated one. We calculated this. We do not have C1 because C1 is a 0. So there's nothing that you're going to get from what? From C1. So we are going to use C2. The velocity at any point over the velocity at the what? At the throat. That is the definition of our what? Match number. The ratio of the velocity at any point along the nozzle to the velocity at the throat. The velocity at any point, if C1 was given, we're going to use that, but C1 is not there. So we're going to use C2 because we calculated this. So you can use this to calculate CC, all right? The speed at the throat. So that is the match number times the speed at the throat is equal to 1 times C2, which is C2. To find this, we're going to divide by N, which is our match number in this case, all right? So that's the speed at the throat is going to be what? C2 which is what? The one that we calculated the speed before. We calculated here our C2. So this one is just a substitution. Our C2 here. Okay, let me just remove this, guys. It's now causing confusion. So this is 785,990, which is just 99. All right, over what? The match number. Remember, we are given this match number. That's why we have to think about this. And the match number is what? 1,3. So that's 1,3 there. So that means the speed at the throat is going to be given as a 604. You're going to get something like 604,608. This is velocity in what? Meters per second. At what? At the throat. So this one, we had to use what? The match number, because we are given that. All right, what about the temperature, the absolute temperature at the throat, TC? Also, we can use our formulas, but I also explained about this, but we also have it from the formula sheet, so it's not a need for us to worry. TC, the absolute temperature at the throat, is given by what? TC is equal to T1 into 2 over gamma plus 1. So the formula is there. So we're just going to take our formula as it is. TC at the throat is given as what? 2 over gamma plus 1, like that. All right, so this is T1 times this. So that's TC is equal to T1. We have T1 originally 873 from the original information. Our T1 was what? 873 into 2 over the value of gamma. Remember, our gamma is 1,4. So that's 1,4 plus what? Plus 1. You take from the information that you are given. So this is going to give us TC, which is 727,5 Kelvin. All right, so this is how we could have calculated the temperature that is at what? The temperature that is affecting at the throat. Okay, so guys, you have to be very, very careful with your information and your formulas. All right, the other part is what? The pressure at the throat. Also, for the pressure, we are given the formula direct. Let us also utilize this space here. So the pressure at the throat, the formula is also given. All right, if we check here, that's PC at the throat is given. This is our formula here at the throat. So we're just going to use our formula as it is. So it states that PC is equal to P1 into 2 over gamma plus 1. All right, e to the exponent of gamma over gamma minus 1. So there we're just substituting our values as it is. Remember, P1 was given as 800, guys. This is 2 over gamma is 1,4. So that's 1,4 plus 1 to the exponent of gamma, which is 1,4 over gamma minus 1. That's 1,4 minus 1. So this will give us the pressure at the what? At the throat. And that will be something like 422.625 kilopascal. Okay, so that is the idea of the question. All right, so I just hope it's clear. I just hope it's clear. Then this one is the last part, which is 2.24. Let me just try to push it this side. Here, this one. All right, I think gonna be able to see there. Here. So on 2.24, they're saying we are supposed to calculate what here? The gas specific volume, that is the gas specific volume at the exit here. So we need the gas specific volume. All right, that's V2 at the exit. And the mass flow rate per second. So we need the mass flow rate per second. So this is the flow rate, this one, the mass flow rate per second. All right, so it's going to be kilograms per second, the flow rate. Give both answers correct to 4 decimal places, the volume and also the what? And also the mass. They are supposed to be correct to 4 decimal places. All right. So how do we calculate the volume at the exit? I talked about this from our volume. That is taken as the volume per watt. Is taken as the volume, which is cubic meters per kilogram. Because the mass is taken per kilogram. So if the mass is taken per kilogram, it follows that V2 is going to be equal to R times T2 over P2 from PV is equal to MRT. I talked about this formula. So you just have to substitute V2 is equal to R, the gas constant, which you are given here as 0.287. 0.287 times T2, the temperature. At the exit, when we calculated this, we got, remember, it was 565,494, the exact or the absolute one, over P2. At the exit, the pressure is what? 175. So this must give us V2 to 4 decimal places. Like I said, you can even fix your calculator to 4 decimal places because they said both values should be to 4 decimal places. So on your calculator, this is it. 0.287 times 565. This is 565,494,494. Everything over 175. So that is going to give us 0.9274. But we can do that on our calculator. Shift, set up, you go to the fix, press 6. So to 4 decimal place, you press 4. Your answer is going to be rounded off to 4 decimal places. It's going to be 0.9274. So this is 0.9274. Like I said, it's going to be cubic meters per watt per kilogram because the mass was not included there. We took the mass as per kilogram. So meaning to say that volume is taken per watt per kilogram of the mass that you shall be given. They will give you the mass, but you have to multiply by that volume that you're given. All right, so that's our V2. Do not forget this value. We are going to need it because here they need us to calculate the flow rate. All right, let me not erase it because we need the flow rate. So to calculate the flow rate, I said it's a combination that you are connecting between the volume and the mass. Between the volume and the what? Sorry, this is the mass flow rate. All right, so the mass flow rate is not about that. This is the one here. Sorry, I was thinking about the other one. This is the mass flow rate. We take it from here, from the area. This one. All right, so let us take our formula back here. So on that formula, it states that area 2 is equal to, that is the area at the exit, is the mass flow rate times the volume at the exit over the speed at the exit. So as we want this, the mass flow rate. So you're gonna just cross multiply. That is 1 times mass flow rate. It's mass flow rate times V2 is equal to A2 times C2. So to find this, you're gonna divide by V2 by V2. So that's, we've got the mass flow rate. But take note, this here, because we are given this as meters per second, volume cubic meters. So it means the area must be in square meters. Remember the conversion from square meters to square centimeters. You're multiplying by 10 to the exponent of 4 to square centimeters. So from the square centimeters now to square meters is the opposite, the reverse. You multiply by what? By 10 to the exponent of -4. Because you are given area in square. Remember, guys, here from our information that we took here, our area was in square centimeters here. This is our area, 7.45 square centimeters, our area 2. So this area must be in what? Square meters. You multiply by 10 to the exponent of -4. So that's the area at the exit, which is 7.45 times 10 to the exponent of -4 times the speed at the exit. Remember, we calculated that. Let's hope I did not remove it. I removed this one. Okay, no problem. Let me just write it down here. So the speed at the exit, remember, we calculated and got something like, it was 785,99 for this value. All right, then everything divided by V2, the volume at the exit. Also, I think I removed this. It's here. This is the volume at the X, the one that we calculated now, 0.9274. So if we do this, we are going to obtain what? We are going to obtain the mass flow rate. All right. So this is going to give us the mass flow rate. That is what we have in that case. All right. And also we have to take note of what the units that, I mean, we have to take note of this part of our units. All right. Meters, square meters, and so forth. Okay. And also you're told to 4 decimal places. So this is what we are simply going to do. I'm just going to bring the calculator here so that, remember, my calculator is already fixed to 4 decimal places. So meaning to say whatever that we have, it shall be rounded to 4 decimal places, times 10 to the exponent of -4. That is, this one is for conversion to what? Square meters, times 785.99 everything over 0.9274. So this is gonna give us the flow rate 0.6314, 0.6314 to 4 decimal places, and that will be kilograms per second. The mass flow rate is kilograms per second if we maintain the units that we are given there. Okay, so these are the typical questions that you might be given. As you can see, that was 20 marks on everything here. That was 20 marks. So I want you to try as many questions as you can, as many questions. Then if there's a challenge, let me know so that we can work that question together on the comment section that's just mentioned the question. And also for your questions to be answered as soon as possible or as fast as we can, you must join the membership. By joining the membership, you can attempt your questions, guys, as many as you want us to work your questions on Power Machines N6 and also Mathematics N6. But for now, that's it, guys, till we meet again.